So what we want to talk about today, we touched on it a little bit with you guys yesterday, but we want to talk specifically about ratios. Ratios are just a comparison between numbers, between two numbers usually. For example, in the classroom right now, I could compare broadband to wood students. We have 4 broadband students in here right now. And 1, 2, 3, 4, 5, 6, 7, 8 wood students. I could write it like that as a fraction, 4 to 8. Or I could write it with the colon, 4 colon 8. Or I can write it with the words 4 to 8, like that. I prefer to write it as a fraction because there are a lot of things that I can do with a ratio that I would also do with a fraction. But any of these other forms work as well. An example of one of those things is I can reduce that. Both 4 and 8 can be divided by what? Not everybody wants plenty of time for everyone to? 4, there you go. So 4 divides by 4 to give me 1, 8 divided by 4 is 2. So a 4 to 8 ratio is the same as a 1 to 2 ratio. Excuse me. Now I can reduce these other forms in the same way. Like here, 4 divides by 4 to give me 1, 8 divides by 4 to give me 2. That reduces to a 1 to 2 ratio. It's just we're used to doing it as a fraction, so there's no use learning a new process for it. Now a note here with this last form, 4 to 8. That applies because we're comparing two totally separate groups. There's another verbiage, another phrase that we might use. It'd be like this, 4 out of 12. When I use that language, I am implying that these 4 are included within that 12. So what this is the ratio of broadband students to total students in the class. You'll notice it's the same ratio because how did I get the 12? 4 plus 8, very good. This is big in a lot of things. If you get into mixtures, solutions, stuff like that, mixing gasoline for any 2-cycle motor, any other chemicals that you have to mix. For some of you guys, you might deal with resins and hardeners that you have to mix. You might have a 3 to 2 ratio, but often as you're mixing, if you know what total volume you want, it might be easier to use a 3 out of 5 ratio and a 2 out of 5 ratio to figure out how much of each component you're going to use. Again, the 5 is the total, and found by just adding the 3 plus 2. Let's look at some other ratios, like the table here in the classroom. If you look at that table, these are 6-foot tables, so those are 72 inches long. They are 18 inches wide. Now the inches divide out. Both 72 and 18 can be divided by such a talkative group here today. They divided by 18. What's 72 divided by 18 is 4. 18 divided by 18 is 1. Now here we'll see one of the differences between a ratio and a fraction. In a fraction, if that were just a fraction, 4 over 1, I would just write it as 4. Good. But a ratio is a comparison between two numbers. I need to keep that 1 there. 4 alone is not a ratio. It has to be 4 to 1. The other thing you'll notice is in the ratios I've created so far, the units are the same on both numbers. Inches compared to inches. Up here, it was students to students. And that is an important quality of ratios. To be a true ratio, both units must be the same. If I have 2 feet compared to 18 inches, that is not a true ratio because it's two different units. Now, fortunately there, I can convert that. 2 feet becomes what? How many inches? 24 inches to 18 inches. And now it's a ratio because the units are the same. Inches cancel out. Both 24 and 18 can be divided by 6. Good. 24 divided by 6 is 4. 18 divided by 6 is 3. Second difference between a fraction and a ratio is exhibited here. If that were a fraction, that would be an improper fraction. The numerator is the top number is bigger than the bottom number. Numerator is bigger than the denominator. I would reduce that to 1 1/3. But it's not a fraction, it's a ratio. So I have to leave it as 4/3 because it's comparing the two numbers. 1 1/3 is not a comparison of two numbers. So since these all have to have, the two numbers have to have the same units or same label, you'll notice that the ratio itself has no labels or units within it. So for this one, length to width ratio, you might wonder, well, what unit does the length and width have to be measured in? Well, because they're the same and they divide out like that, it doesn't matter. You know, for every 4 units of length, there is 1 unit of width. Doesn't matter whether this is 4 inches of length for every 1 inch of width, or 4 feet of length for 1 foot of width, or even 4 centimeters of length for every 1 centimeter of width. Whatever units you measure those in, it will work out to a 4-to-1 ratio. So then the next logical question is, what happens if the units aren't the same? Let's say we're going to send Jasper on a road trip. Not that I want to send you away for any reason ever, Jasper. Jasper goes 365 miles, and it takes him 7 hours. There is no way I can convert miles into hours here, or hours into miles. There's no way I can give them the same unit or same label. So this is not a ratio. It is what is called a rate. That is the first difference between a rate and a ratio. Is a rate compares two numbers with different labels or different units, and a ratio compares two numbers with the same units. Now going back up here, what we created here, the second number or the bottom number in this form is a 1. That is what is called a unit ratio. Bless you. If it happens to work out that way, we'll express a ratio as a unit ratio. But we have no problem leaving it like this, as 4-to-3. It doesn't always have to be to 1. There are a couple of ratios out there that we'll look at that do typically get expressed as unit ratios, and we'll mention those as they pop up. With rates, however, we almost always express them as unit rates. So what that means is the second number, or the denominator of the fraction form, needs to be changed to 1. To do that, we divide by the numerical value of the denominator. In this case, that numerical value is 7. So we divide both the numerator and denominator, or since this is a rate and technically not a fraction, both the bottom number and top number, by 7. Well, 7 hours divided by 7 is just 1 hour. 365 miles divided by 7 is, what is that, 52.142857143 approximately miles. Does that work? Okay, now a couple of things. First of all, I'm not going to take it out to, 9 digits. We'll probably round that off to 52.14 or maybe even less. Second, because this is a unit rate and it's 1 on bottom, in a rate, we do often eliminate that appearance of a fraction in the numbers. We might write it like this, miles per hour. So the appearance of the fraction form is pushed off into the units. In fact, we might even go a step further. and we will 52.14 mph, where the appearance of the fraction is gone altogether. But we do have to remember what it really stands for. For example, let's say on this trip, Jasper gets 22 mpg. Would have expected better out of you. But what does mpg stand for? Miles per gallon. So 22 mpg means 22 miles for every 1 gallon. Whenever you see 22 mpg, you need to be thinking this, because when we go to calculate with it, this is the form it needs to be in. So let's look at some examples of rates and ratios. Let's start with rates. We looked at the miles per gallon, miles per hour. You might look at a motor that turns 40,000 revolutions in, let's go 5 minutes. Little hamster refused to turn the wheel there for a second. So this, as a rate, 40,000 revolutions over 5 minutes. What do we do to reduce that? We can divide by 5. Turn it into a unit rate. Divide by whatever that number is in the bottom number. So 40,000 divided by 5 is 8,000 revolutions. 5 divided by 5 is 1 minute. So that is 8,000 revolutions per minute, of course, is RPM. Just a little bit of a side note, a lot of people will say RPMs. It's not revolution per minutes. That would be RPMs. It's revolutions per minute. So it is just, technically it is just RPM. I don't get real upset about that one, but some people do get upset about it. Other rates that you might run into in construction, actually even for you guys in broadband, it can be a little bit of an issue. You'll worry about structures and loading and stuff like that. When we get into vectors, we'll look at loading, poles, utility poles and stuff like that as well. You worry about things like you might have 800 pounds spread out over 16 square feet. Now, of course, we're going to divide by the 16. 800 pounds divided by 16 is 50 pounds. 16 square feet divided by 16 is 1 square foot. So that is 50 pounds per square foot, or PSF. Look familiar? One that most of you have probably already experienced might be this one. You get paid $480 for 40 hours. We're talking gross, not net. We'll leave your taxes alone for now. Dividing by the 40 to get that into a unit rate, that's 1 hour on bottom. 480 divided by 40 is $12. So that is $12 per hour. Those rates, I'm sure you can see all around us. They're everywhere. You guys can look at signal transfer rates. How many megabytes per second, megabytes per minute, stuff like that you're looking at. They're everywhere. Let's go back to ratios. We're going to have some fun. And you guys are going to use your imaginations because I'm going to draw pictures. And there's a very good reason why I'm a math teacher and not an art teacher. I'm smelling peanut butter back there again, guys. Anybody want to guess what this represents? There you go. It's gear ratio. Is it two suns hugging? A gear ratio is defined to be number of teeth in the driven gear over the number of teeth in the driving gear. So anyway, looking at this, the big one has how many teeth? 12, and the little one has 8. How do we know which one's driven and driving? Well, I need more information than what I gave you here. So back to my amazing art technique. Pretend that's a small electric motor. Now, if I separate the two gears, one of them will keep turning and one will stop. Which one will stop? The small one, the 8-tooth gear. That is the driven gear. It is being driven by the other one. It's only turning because the other one is driving it. The 12 is the driving gear. So it is an 8 to 12 gear ratio. And of course, that can reduce, dividing by 4, to a 2 to 3 gear ratio. Now, in a gear ratio, that ratio represents a lot of things. It's the ratio of teeth. It's also the inverse ratio of the RPM, the ratio of torques, among other things. Something Jasper might be a little more comfortable with. Pulleys. Pulleys have no teeth. So if we look back at why we counted teeth on the gears, for two gears to mesh together, the teeth have to be exactly the same distance apart. So by counting teeth, all we're really doing is measuring the size of the gear. Actually, the circumference, the distance around the circle. Well, for a pulley, there's no teeth to count, but the circumference is directly related to its diameter. So we can just compare the diameters of the circles. Let's say this is a 6-inch pulley and this is a 16-inch pulley. Now again, we need to know which one's driven and which one's driving. So once again, pretend that looks like a powerful little electric motor. If I cut the belt, which pulley stops? The 16, so that is the driven. So the driving is the one connected to the power, is the 6-inch. So the inches cancel out. 16 divided by 6, or 16 and 6 both reduced by 2 to give me an 8 to 3 ratio. Since we're having fun drawing pictures, let's try a more complicated one. Pistons, there we go. We're going to be looking at a compression ratio. They do kind of, yes, the push pops. So anyway, compression ratio is the expanded volume compared to the compressed volume. The expanded volume is when the piston's at the bottom, it's called bottom dead center, the bottom-most portion of the stroke. So the volume above the head of the piston is the most it can be. So let's say that's 480 cubic centimeters. Compressed volume is what they call top dead center. The piston's at the very top of the stroke. And the volume in the cylinder above that piston head is the smallest it's ever going to be. Let's say that is 60 cubic centimeters. So our expanded volume is 480 cubic centimeters. Compressed volume is 60 cubic centimeters. Now the cubic centimeters cancel out. Both 480 and 60 are divisible by 60. Gives us an 8-to-1 compression ratio. Compression ratio, by the way, is one ratio that is almost always expressed as a unit ratio, even if it doesn't work out nice and neat like this one. Other ratios. We'll talk about this one a little bit more when we talk about percents. We're going to talk about grade. A grade defines how steep the ground is. Grade is defined as rise per 100 feet of run. So let's say this rise here is 12 feet. That's a 12 out of 100 grade, or 12% grade. One that's going to be pretty important for you guys in woods. Actually, two of them I'll bring up here. Slope and pitch. Do you guys know the difference between slope and pitch? What's that? Well, let's say that we have this roof here. We're going to give it a span of 24 feet to make this easy on us, and a height of 6 feet. We talked about this a little last semester, but we'll bring it back. Slope is rise over run. The rise over here is 6 feet. The run is not 24 though, it is, the distance from one end to that peak, which is 12 feet. So it's 6 feet over 12 feet, or a 612 slope. Slope is always listed as out of 12. That's why I did the 24, so that would work out neatly. Pitch is slightly different. Pitch is height, or total rise, over span. So the height is still 6 feet, but the span is 24 feet. That reduces to a 1/4 pitch. Anybody remember why there's a difference? Well, slope is used for building trusses. If you're building trusses, you're worried about the angle of cuts on your top cords and all your angled pieces. That 612 slope, when we get into our trig functions, that 612 slope is what we use to figure the angle of that cut. Pitch is used if you're building a traditional beam and rafter roof. So if you have your sidewalls, pitch is the fraction of the span that the ridge beam has to go above the sidewalls. So let's say that this is a 40-foot span, and you have a 1/4 pitch. Well, what is 1/4 of 40? 10, right? So what that means is that ridge beam, the top of that ridge beam, has to be 10 feet above the top of that wall. 1/4 of the span. Other ratios for you guys in broadband in your electronics. You guys dealt with transformers yet? Yeah, a little bit. Of course, you know, in a transformer, you got primary coils and secondary coils. How do you measure a transformer ratio? You guys remember it all? Let's say your primary coils are 200 turns. Your secondary coils are 500 turns. Your transformer ratio is usually the number of turns in the secondary coil, the number of turns in the primary coil. So that's 500 over 200, which of course reduces to a 5-to-2 ratio. That's also going to be the ratio of the input voltage to output voltage. Your secondary coil has more turns, so this is actually what's called a step-up transformer. It'll actually increase the voltage. Now, just a little side note from electronics, if you increase the voltage, what has to decrease? But you know, what has to stay constant? Power. Power is always conserved. So when you have a constant power, if the voltage goes up, what must go down? What's the other component of power? Current. The current has to go down. So if the voltage goes up by a ratio of 5-to-2, the current goes down by a ratio of 5-to-2, or actually the inverse ratio, 2-to-5. When you look at a bridge ratio, have you guys looked at electrical bridges yet? No? An electrical bridge is just a type of circuit that allows you to very precisely determine a current. Usually one of these resistors, we're going to say this one here, is a variable resistor. We're going to call that Rx. Over here we have R1 and R2. I'll call this one RY. The bridge itself actually goes across between these two sides of the circuit. Then, of course, there's a voltage source that comes in like that. What the bridge is for, now you guys have you worked with resistors, and you know that a standard resistor often has a tolerance of plus or minus what percent? 5 is actually 5 is a more precise one. You're looking at 5, 10, 20%. That's quite a bit of error. If you want an exact current to flow, your standard resistors aren't capable of giving you that exact current. So if we want to control the current that flows into a device, we use a bridge. The bridge ratio is either R1 to R2 or R2 to R1. If that ratio, R1 to R2, matches the ratio on the other side of the bridge, RY to RX, that's why this is a variable resistor, is you can change that resistance until, you guys know variable resistors are called potentiometers. You can vary the resistance to balance that. If those two ratios are equal, zero current flows over here. If you increase this resistance, current will start to flow that way. If you decrease that resistance, current will start to flow the other way. So you can actually cause current to flow either direction. Any of you guys into model trains, either group? Anybody ever had a train set when they were a kid? Watch it go around? Yeah. You had that knob. If you turned it this way, the train went forward. You turned it this way, the train went backwards. That's exactly what it is. It's a potentiometer. That's a variable resistance. That dial you're dealing with is controlling this resistor in a bridge. You turn the resistance in one direction, current flows this way and the train goes forward. Turn the resistance in the other direction, current flows the other way and the train goes backwards. That's why you always had to unplug your train set, because the current is flowing no matter what. So that's why they would heat up and there were fire hazards. It wasn't like the on-off switch actually shut off the current. It controlled what direction the current flowed. Okay, other general ratios that might be of concern to you guys. One that'll probably be a concern to all of you at some point. Debt to income ratio. I know financial stuff is what everybody wants to talk about, but a debt to income ratio is really what determines whether you get a loan or not when you go to apply for a loan. You hear a lot of talk about credit scores. Credit scores are really not, unless you have a really, really bad credit score, it's not a determining factor whether you get the loan. Unless you're down like below, if you get below like a 620 or 625, then that usually means you've had some credit problems in your past and they'll deny a loan. But if you're above that minimum level, the credit score really determines how good of a rate you're going to get. So like if you're from usually 670, 625 to 675 is considered high risk. So you're going to pay a little bit higher interest rate. You go to get a car, you might be paying 6 or 7% interest on that car. If you're below that 625, you're going to have to go to a super high risk lender. I had a student here last year, I think was paying 18.9% on a car loan. I mean, that's literally credit card rates is what they're giving them. So, I mean, you can't afford to buy anything more than about $3,000 or your interest is, a couple $100 a month. If you have that credit rating above 675, then that's where you get into the good rates where you might get a 3 or 4% car loan. If you get above, I think depending on the bank, 710 or 725 is the cutoff where you get the 1.9% auto loans that they were offering a year ago. You look like you've got a high rate loan out there for your car. Yeah? Not too bad? Okay. So that credit score just helps you determine your rate. It's your risk. It's your debt to income ratio that actually helps the bank evaluate whether you have the income to repay that loan, whether you're going to get it or not. So let's say your income, working 160 hours per month at $20 per hour. What's your gross income? Hold yourself back. Plenty of time for everybody to participate. How do we figure that out? You guys have never figured out your own paycheck? $3,200. There we go. We just multiply them out. $3,200. That is your gross income for the month. Your debt. Well, do you guys want to own a car? Okay, that's probably a silly question. How expensive of a car or truck do you expect to own? Right. $9,000? $90,000? That would be approximately $2,000 a month. That's more than your income. So, well, more than half your income. They're not going to give that to you. $45,000 would be just under $1,000 a month. They're probably not even going to give you that. Well, let's do it. Do it. $45,000. That's $1,000 a month. Let's be generous with you. We'll make it $900 a month for your car. Credit card? A $5,000 car is right around $100 to $110 a month. Anyway, you have any credit cards out there? Probably going to have to if you can afford to make that payment, right? Let's just put $100 on credit cards per month. Let's say that your purpose of figuring this out is you want to buy a house. You add that up, that's $1,000 per month so far. Right now, your debt to income ratio is 1,000 to 3,200. Both of those divided by 100 gives me 10 to 32. Both of those divided by 2 gives me a 5 to 16 ratio. The magic number for most banks that they use is 1 to 3. Is 5/16 less than 1/3? Yeah, 5/16 is about 0.3125. 1/3 is 0.333. So it's less than 1/3. That means you're good to go, right? Well, so far, but if you want to get that house loan, they've got to figure in what that payment would be. How expensive of a house do you want to own? The double wide's about $60,000. 13 bathrooms, 8.2 million. That's it. Well, if you're going to put it in a trailer court, maybe, but you got to have the land and the septic and well and everything with it. I go 70 grand. Okay, $70,000 loan is going to cost you about $350 a month. If you add that to your 1,000, you're now at $1,350. So that's $1,350 out of 3,200, which is 135 out of 320. Both of those divide by 5. What is 1,350 divided by 5? 27 over 64. 27 64ths is 0.4219. Is that bigger than 1/3? Yeah. They're going to give you that loan? No. That's more than you can afford. To get to 1/3, 1/3 of the 3,200, by the way, is 1,067. So how much money do you have freed up to make on a house payment right now? 67 bucks. Anybody want to guess what they're getting for 67 bucks? I said it's about 14 grand. A 30-year loan, which they won't give you on something that cheap, you'd be looking like 14 to 16 grand. So you have a 2-story cardboard box sitting on a loading dock somewhere. That's what you want? Hey, nothing wrong with that. Everybody's got to have goals. The point here is, just because you can afford that car payment and you can get that car loan, doesn't necessarily mean you should get it. Because that $900 payment, that's probably locked in for 6 or 7 years. I've seen car loans now for as long as 8 years. 5 years from now, you want to buy a house, you can't afford it because your payments are too high. So just because you can get the loan and you can afford those payments doesn't mean you should. You got to leave room for those future goals. Okay, so for you guys in broadband, I've got a couple of things I'm going to give to you. Your homework, I'm going to give you 2 things. I'm going to give you a packet that has Unit 28 in it. I want you to do Unit 28. And I'm going to give you another packet. On page 252 of that packet, I want you to do 1 through 12. For those of you in Woods, I'm going to give you, this is in your big book. Page 133. Actually, take that back. I think they changed the page on me. Page 154. Exercise 5-2. 1 through 31, the odd. And on page 163 through 164, this is out of the unit review exercises, 17 through 31, the odd. Broadband, I've got a quiz to give you guys to take with you to work on as well. I'll get that out to you. You don't want it?